So this is our program so far with some examples of the move instruction, and I just want to go over this one more time just to tell you that this right here, this directive that reserves an integer in global segment is an equivalent of declaration of global variable in C. The variable name is value, it's initialized to 0, and its type is integer. So this integer corresponds to D word, a double word in a Microsoft Macro Assembler. So this is memory allocation directive. This is the label that identifies location of this integer in memory. And of course, this value is initializer, like we can do it in a C program statement. And this offset allowed us to take the address of this integer and load it into the register. So basically, the value is a label that assumes the address of this integer in memory, and when we take it with an offset operator, this address is stored in register ESI. And then we again use this address now available in register ESI to take immediate value 10 and store it in this memory location. So basically this gets updated with the new value 10. Let's take a look at examples of some arithmetic instructions. So increment and decrement arithmetic instructions. We can try something similar to our move instructions. For instance, I can just change this to this move, change to an increment. Increment location in memory at this address. It's like we can write some pseudo code here and say something like plus plus, right? So in C this would be plus plus, and we're adding it at location specified by register ESI. So we're incrementing this by 1, whatever the current value there is. And of course we can also use decrement instruction. This time I'll try to decrement register EAX. So this is like if you had a variable named EAX in your program and you're decrementing its value. So just basically plus plus and minus minus work as increment and decrement. Another example is add, subtract, add. So there's this is an addition instruction. It requires two operands, source and destination. Source and destination are added together, so it's like destination plus source, and then the result is stored back in the destination. So let's try something like this. Again, I can just take the same location and change move to add. Okay, so now we're adding 10 to whatever is currently stored in this memory. And of course we can use registers. Now we can also add EAX, for instance 1. Okay, so it looks very similar to incrementing by 1, but the difference is, and here's some information, is that some instructions can be longer and some instruction can be shorter. So let's take a look at the sizes of our instructions in memory. I already, by the way, let's also add this pseudo code right here. So this would be like taking whatever is stored at the address ESI, and we're adding 10 plus equals 10. Okay, so that's an equivalent of a C expression like this. And here, once again, this would be equivalent to saying EAX if this was our variable in C, and plus equals 1. So now here it's the difference between these two. There are some differences, but different instructions could also occupy more or less space in memory, and I'd like to show you this. I already have this breakpoint, which is right at the top of my main procedure, and I will build this just to make sure that, of course, everything compiles fine. And I'm going to press F5 to start debugging session. And so my registers are shown right here, and the program is loaded into memory. And so instead of executing it, I would like to show you a disassembled view of this program. So anywhere in source file, if you right click and go to disassembly like this, right click in the source file, it opens another window. I'll try to resize everything to show you. So you have some options here. For instance, currently the source code lines are shown in this window as well. So each source code line is shown here. And then in this current format, we're observing the actual instruction that was compiled. So it's showing, disassembler still shows a very similar mnemonic. However, it even provides us the actual address. This address of this integer is now shown as 0A03 and so forth. We can change this format a little bit. For instance, if you right click in the disassembly window, you can say that I don't want to see the source code. Okay, so now it's just a disassembled view. And if I want, so it's because this is assembler and this is assemble program disassembled, you can see that everything is very much look-alike in both of these views. But now the next step would be to right click in this assembly view and say show code bytes. Okay, so the code bytes actually display how much space in memory each instruction occupies. So this first instruction that uses immediate value 5 and address of this variable looks like this. And you can see that this immediate value 5 is actually encoded directly inside the instruction. So these 4 bytes right here, these 4 bytes of this instruction represent this immediate value, right? So this immediate value stored not somewhere independently in memory, it's stored directly as part of the instruction. This of course makes this instruction so long. For instance, we can count the bytes. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is this correct? 1, 2, 3, 4, 5 and 5. Yes, so this is 10-byte long instruction, quite a long instruction. And in comparison to this, decrement EAX instruction is taking only 1 byte in memory. So you can see that these instructions that we were writing to experiment with different parts of the syntax, when they're translated by assembler into actual instructions, these instructions have different sizes. So this is to be expected, and this is what we call complex instruction set computer architecture, because instructions can be occupying variable number of bytes in memory. Each single one of them has the address in memory, but their sizes are different. And this would be versus RISC architecture. This was CISC, complex instruction set computer. The opposite of this is RISC, reduced instruction set computer architecture, and that would be the case where each instruction is exactly the same size. Typically on a 32-bit platform, each instruction will be 32 bits in size, and on a 64-bit platform, each instruction size is 64-bit. Okay, so that's a different story, but here you can see that these instructions are occupying different sizes.